Hello everyone, this is Prajakta Churve. Today I am going to discuss the first stable p-type 2D semiconductor material, tin oxide, which is considered as the new emerging technology in the field of semiconductor and electronic devices. These are the outline of today's topic. We will start off with 2D materials. What are they? What are their needs? We will focus more on p-type material as we have the number of n-type material available, and in order to have the semiconductor devices to work more fast, we need both type of material, the n-type material as well as the p-type material. We compare between the 2D and 3D and see what are the advantages of 2D transistor over 3D transistor. Then we move on to the tin oxide. What is its electronic configuration and what is the uniqueness of tin oxide? That is why it is chosen as base to fit for p-type 2D semiconductor material. Then we will see the manufacturing process of tin oxide, how it is made, the current state and the future challenges, and we will end up with the conclusion. 2D materials are made up of one layer, the thickness of just one or two atoms. The figure here shows the structure of 2D material. As you can see in the figure, it consists of a single layer of atom. That's why it is sometimes referred to as a single layered material. Now we move on to see the need of 2D p-type material. We have the number of materials such as graphene, molybdenum, disulfide, borofine, but these are the material that only allows the movement of negative charge carrier, that is electrons. But in order to have the electronic devices, we need a semiconductor material that allows the movement of both type of charge carrier, the negative electron and the positive charge carrier known as holes. Even though we have the graphene, which exhibits a high mobility, the lack of band gap makes it almost impossible to develop into the digital FETs. Also, in the case of molybdenum disulfide, the charge carrier trap makes the mobility of molybdenum disulfide lower. Traps are the impurity or the dislocation that can trap the electron or hole and hold it until the pair is complete. That's why reduces the mobility and hence the speed. Let's talk about the difference between 2D and 3D. Why we have chosen 2D or 3D? We have the number of 3D material. The most common one is silicon, which composes of multiple layers on a substrate of glass, while the 2D material consists of single layer of atom. As we have single layer, the charge carrier can move only through that direction, while in case of 3D material, the charge carrier can bounce around any direction. That's why the transistor made with 2D semiconductor material could be 100 times faster than a regular 3D device. As we have the single direction in case of 2D material, there will be a less friction, meaning the processor will not get as hot as normal computer chips. Also, the transistor made with 2D semiconductor material requires much more less power compared to 3D. This is the boon for mobile electronics that have to run on low battery power. These are the advantages of 2D transistor. As described earlier, the 2D material have only single layer of atoms. The charge carrier can move only through that direction. Hence it is much more faster than a conventional 3D. There is a less friction among the charge carrier as all the charge carrier are moving along in a single direction. It will run on a low power. It also requires a less area. If we have a transistor made up with 2D material, we will produce a much more powerful processor. Now moving on to the tin oxide. Tin has an electronic configuration of 4D10 5s2 5p2. In tin monochalcogenides, it loses its 2,5p electron to the more electronegative atom. Chalcogenides are the element consisting of anion and are more electropositive element. In tin, the 5s electron do not participate in the bonding process and they constitute a lone pair. In tin oxide, these lone pair points toward the interlayer spacing and result a smaller gap between the tin oxide layer. This lone pair activity and small gap between the two layers makes the tin oxide unique than the other material, as the other material have a larger gap in between the two layers. The figure here shows the structure of tin oxide. Figure A shows the structure of tin oxide. Figure B shows the interspacing between the two tin oxide layers. If we compare this spacing of tin oxide with other material, the tin oxide spacing is much lower than the other material. And the figure C shows the 2D structure of tin oxide. Now let's talk about the manufacturing process of tin oxide. Tin oxide is grown layer by layer on a sapphire and silicon dioxide substrate using a pulse laser deposition method. The number of silicon oxide layer is controlled by controlling the number of layer shot during the deposition process. The pulse laser deposition is a physical vapor deposition technique where a high power pulse laser beam is focused inside a vacuum chamber to strike the target of material that is to be deposited. This material is vaporized from the target which deposit it as a thin film on a substrate. This process can occur in an ultra-high vacuum or in the presence of a background gas such as oxygen, which is commonly used when depositing oxide to fully oxygenate the deposited film. The figure here shows the process of PVD. Now, what is the current state and future challenge in this topic? The potential for the 2D material, such as graphene molybdenum disulfide, as an alternative to the 3D silicon, raises hope for the smaller, faster, low power transistor. Now, today we have everything. We have P-type, N-type, 2D semiconductor material. If these materials are mated together, the things will go forward much more quickly. Now the future challenge is we have to mate this tin oxide P-type which carries holes with the N-type which carries electron in a transistor. It opens up the possibility of building power-saving two-dimensional complementary logic circuit, the ones which we use in a today's microprocessor. Now the next step in this research is to build a CMOS complementary metal oxide semiconductor using this new type of 2D semiconductor. From the above discussion, we can conclude that tin monoxide as a first stable P-type 2D semiconductor material ever in the existence. Tin monoxide as a best P-type 2D semiconductor material which is much faster than the common 3D material such as silicon. It requires less area, runs on the less power and dissipate the less heat. This breakthrough in semiconductor material could lead to much faster computer and mobile devices such as smartphone.